question. Okay, so as we can already see in the previous two examples, right? The first one looking at the breakdown from combustion. Sorry, the compressor. They provide us with some information there. They provide us with the value for the combustion chamber, the turbine, as well as the nozzle. Whereas in the second example, you treat the engine as the whole complete system. So there is we neglect anything happen in between. So we just treat it. The air goes into the engine. The air receive energy from the combustion chamber, combustion process, and then the air exit the engine. So you find the thrust. So for the third question, it is more complicated. We have a case here, a typical airplane, Fiat G91Y. Okay, it is a single-seat strike and reconnaissance fighter. It is powered by two General Electric engine, J85 GT13A turbojet. Right. So each of the engine rated at 12.12 kilonewton. So imagine one engine rated at 12.12. So if you have two engine, you just time 2 in terms of the engine rating, in terms of the thrust produced. The aircraft is operated at an altitude of 9,150 meter. Okay, it's not at the sea level, it's not on the ground, it is cruising at an altitude of 9,150 meter. Okay, given here ambient conditions at 32 kilopascal as well as temperature of 240 degrees Kelvin. So it is at the freezing condition. So sometimes if it's not given the value of the altitude, value of the temperature as well as the pressure, you may assume at the sea level condition. So sea level condition will be given normally in the formula sheet, where some value of the temperature as well as the pressure at the sea level. Okay, so but here it is given at an altitude of 9,150 meter. So it also provides us with the pressure ratio. Okay, so the pressure ratio given here, pressure ratio for the compressor is 12, right? If you still remember our discussion in the compressor, the higher the compressor ratio, the better the engine. Okay, but for this particular type of aircraft, the compressor ratio is just 12. And the temperature at the turbine inlet, the TIT, turbine inlet temperature, is provided as 1,400 degrees Kelvin. Okay, the aircraft speed V1 is 310 meter per second. Whenever, as I highlighted earlier, whenever you have the information, when you read the information, you straight away put down the information that are provided in the question. Okay, assuming ideal operation. So in this question, they already give you, and this is in the question itself, assuming ideal operation for all components. So the all components meaning that the inlet, the compressor, combustion chamber, the turbine, the nozzle, it is all operated at ideal operation. Okay, and we also assume unchoked nozzle, right? The nozzle itself is unchoked. If it is choked, there will be different treatment for the problem. Okay, and given the constant specific heat in all processes, specific heat for air being given here, Cp 1005 joule per kilogram Kelvin, and the specific heat ratio gamma equal to 1.4. There are cases gamma is also given as a different value. All right, so in this case, we assume the specific heat ratio for the air is 1.4. The heating value for the combustion chamber, okay, the Q is 42,700 kilojoule per kilogram. Okay, there are six things need to be identified in the question. The first one, you need to find the fuel to air ratio. Okay. The second one, the velocity of the exhaust gases. Okay, exhaust gases, the VJ or V5, depending on how you treat the question. So normally you can use VJ, and then or V5 lah. And then the air mass flow rate, the M dot A. Okay, the propulsive efficiency, okay, zeta P, the thermal efficiency, zeta TH, and the overall efficiency, the zeta O. So if you look at the earlier slides on our theory on the gas turbine performance, all right, I think in lecture number 5 or number 6, you may find out there are equation already provided. So, but in this, normally in the examination, we will provide you with the formulas. All right, so the formula related to propulsive efficiency will be given, the thermal efficiency will be given, the overall efficiency will also be given. Just a matter of putting the right numbers in. Okay, let us do step by step. But before we go into the finding A, it's best practice to jot down all the information provided. Okay, the given data from the question. The question doesn't ask us to write down the assumption because the assumption has already been highlighted in the question. So you just have to jot down all the information provided. It is not compulsory, but it is a best practice to jot down all the information. The first one is being given is the thrust. The thrust, even though in this question, it is highlighted earlier that there are 2 engines, right? But we are going to calculate for 1 engine, okay? 1 engine for the fuel to air ratio, 1 engine for the velocity exhaust gas, because the velocity exhaust gas as well as the fuel to air ratio for the 2 engine are the same, okay? I hope nobody will just time 2 for the thrust. And the flight altitude is 9,150, at which the ambient pressure and temperature are also given, 32 kilopascal for the pressure, and the TA is equal to 240 Kelvin, degrees Kelvin. The compressor ratio is pi C, okay, equal to 12, right, being given. And the turbine inlet temperature also being given. The maximum temperature in the engine is 1,400 degrees Kelvin. The fuel heating value, okay, is 42,700 kilojoule per kilogram. So make sure all the units are there. Okay, don't leave the unit behind. Okay, and the flight speed, okay, or F1 or F not equal to 350 meter per second. Specific heat is 1005. Don't forget the gamma is given as well, 1.4. Right. So even though it's not being written, it's not being asked for you to write down the assumption. These are the kind of assumption that we can treat for this particular problem. Steady operation, air standard assumption, air as an ideal gas, okay. Kinetic and potential energy are negligible. The turbine work output is equal to the compressor input. Right, let us look into the diffuser. Since all the processes are ideal except at the diffuser, the total temperature equal to, okay, total temperature TO2, okay, equal to TOA. TOA, where TA plus the kinetic energy of the air, right? So you will put down the numbers there. You will get TO2 as 287.8 Kelvin. The total pressure is calculated from the relationship. Okay, we have this relationship, right? Normally being given in examination. Okay, where you will get PO2 to be 60.4. Alright, kilopascal. Right, that is at the diffuser. Let's move on to the compressor. Right, at the compressor, compressor outlet pressure is obtained from this relationship where we have the formula where PO3, okay, PO3 is the compressor outlet pressure. Okay, we have the compressor compression ratio given as 12 times PO2 that we obtained earlier. Okay, and then we will, which is also equal to PO4. Okay, so the temperature at the outlet can be obtained from the relationship. Okay, TO3 divided by TO2, and this formula is normally being given. Okay, you will get the value of TO3 to come out to be 587.5 Kelvin. Okay, so basically we already obtained the value at the compressor outlet and the value of the temperature at the compressor outlet, right? Then in the combustion chamber, right, we assume the combustion chamber to be steady. The pressure is almost constant, right? So the fuel to air ratio, okay, there's a formula there to find this fuel to air ratio. Okay, you will get, you put down the numbers, okay, and you will get value of the fuel to air ratio of 0.0198. Okay, and in certain cases, later on in your fourth year in the air breathing engine subject, we will ask you to use a standard chart, and there will be a chart where you read down the temperature, you read down the certain values to get this F value from the chart, right? But for this particular example at this level for propulsion subject, we will use a standard formula, okay, because there are a lot of assumptions. When we go into more realistic problem, you cannot use this particular expression where you need to use a particular fuel to air ratio chart. Okay. Assuming equal work in both the compressor and the turbine and equal specific heats, then you will then be able to find the temperature at 0.5, where temperature at the exit of the turbine and going into the nozzle, and the pressure at the outlet of the nozzle is obtained as follows this expression, right? And you will put the numbers in, you get the PO5 equal to 317.86 kilopascal, okay, which is equal to the PO6 because we assume that the work in both the compressor and turbine and equals specific heat, right? At the nozzle, finally at the nozzle, for an isotropic flow in the nozzle, the temperature ratio within, let me just move back. Okay, yep. The temperature ratio within the nozzle, okay, TO6 over T7 equal to PO6 over P7 to the power of gamma over gamma minus 1. When you put down the number, you will have the T7 to become 563.6 Kelvin, right? So then you can get the second part of the question, which is the B, to find the velocity of the exhaust gas, Vj, where Vj equal to 1044.34 meter per second. Alright, so that's only part B. Part A just now, the fuel to air ratio, the F value. Then the Vj. And then you need to find the mass flow rate. Okay, so since the thrust force is for unchoked condition, right, is expressed as this, right? So you have the mass flow rate for the air, okay, 1 plus F with this value. The air mass flow rate can be obtained here, where we have the value, this symbol should be F, not T. I'm very sorry. I will correct it when I put down the notes later on. You get the mass flow rate for the air is 16.06 kilogram per second. And the fuel mass flow rate denoted by MF, okay, you will get the fuel mass flow rate to be 0.317 kilogram per second. And then to continue to find the fourth item, Okay, the propulsive efficiency, right? So this equation for propulsive efficiency normally being given, right, in the formula sheet, you will get a value of 45.97